Dear students, in this lecture we will discuss some numerical problems on mesh analysis and star delta transformation. So let us start with the first numerical. In this numerical, there is one circuit given in which we have three meshes basically. You can see there are three meshes, mesh 1, mesh 2 and mesh 3. So these three meshes uh, uh, will give us three uh, algebraic equation in terms of the unknown parameters, and unknown parameters in this are basically the mesh currents. And as per the statement of the question also, we have to determine the mesh current in each mesh of the given circuit, right? So there are three voltage sources connected here, and then we have resistances connected here. Now, the first thing that you will do is you will mark all the nodes basically, as I have already done: A, B, C, D, E, F, and G, and H, like this. The second thing that you will do is you will mark the direction of current in each branch. You can assume any direction as per your convenience. That is totally up to you. However, I have taken the direction as I am showing here, right? So now the direction here in this is like this. Okay. So the third thing that you will do is you will uh, assume some current flowing in the mesh and its direction. So I'm taking the clockwise direction here. You can take anti-clockwise also. So let us say this current is I1 in this case, and then we have the second mesh. In this also, I will assume the clockwise direction, and this current is, let us say, I2. And then in third mesh also, I'll take the same direction, and it is I3, for example. Okay. So because now this branch G, H, A, B, it is an independent branch. So this I1 current is assumed to be flowing in this particular branch here, I1. And then I'll take the I2 current here. This is the independent branch. And then I'll take this I3 current here, right? And when this I1 current will, this is the I1 current actually. So it is coming to this junction B, and it will divide into I2, and the rest of the part is I1 minus I2, which will flow in this particular branch here. Similarly, this I2 current when will come to junction C here. So I3, and then you have like I2 and minus I3 current is in this branch. Okay, now we will apply the KVL in each mesh, and we will determine the KVL equations here. Now it is already written here. So when we apply KVL in mesh A, B, G, H, A. Now how I have written this as A, B, G, H, A, why not something else? Because the direction of this current is clockwise. So it is going like A to B, B to G, G to H, and H to A. This is how it is flowing. Similarly, in this mesh 2, we have B to C, C to F, F to G, and G to B. And then we have last mesh similarly. So let us start with 100-volt source. So in 100-volt, you can see the direction of this current is upward, and the direction of voltage is also from minus to plus. Both will be matching. So we have taken it as positive, right? Then this current here and this branch current both are matching here. So for matching current, I'll take negative. Okay, so the value of resistance is 4 ohm and the current is I1. So the total drop here is for I1. And then you have the current here is from B to G. And in branch also current is from B to G. Both currents are matching. So I'll take the sign as negative. The value of resistance is 4 ohm. And the total current is, this branch is I1 minus I2. And then this current is flowing towards the positive terminal of the battery. So it is opposing the standard direction. So current is going like this, but actually the direction of voltage is like this. So I'll take it as minus here, right? So on simplifying this equation, we have got this equation number 1 here, right? Similarly, we will apply the KVL in mesh B, C, F, G, B. So this is our B to C, C to F, and F to G, G to back to B, right? So we'll apply KVL in this case also. So the KVL equation of this mesh would be given here. So let us start with this minus 4 ohm resistance. We'll start with this minus 4 ohm. Sorry, not minus 4 ohm. It is 4 ohm resistance. So 4 into I2 would be the voltage drop. But as you can see, the direction of these two currents is matching. So I'll take it as a voltage minus 4 I2. So it is minus 4 I2. Similarly, we have rest of the values here, right? And when this current is flowing here in this branch, when we match these two currents, so branch current and this current, so both are matching here. So we will take it as negative, and the resistance value is 4 ohm, and the current is here is I2 minus I3. So it is I2 minus I3. Then we have, uh, let us come to this voltage source. So here the current is flowing from minus to plus, and the standard direction is also from minus to plus for voltage. So I have taken it as plus 20. Now, then let us come to this 4 ohm resistance here. So as you can see in this 4 ohm resistance, uh, this current, this I2 current, mesh current is going upward, and the current in the branch is coming downward. So these two currents are not matching. They are not matching. They are anti-parallel. So the value of this is 4 into I1 minus I2, because the net current in this branch is I1 minus I2. Okay. Now we'll simplify this equation. On simplifying this equation, we have got this equation number 2 here, right? So 4 I2, 4 I2, and 4 I2, it is minus 12 I2 here. Then we have 4 I1 like this. So we have got equation number 2. Similarly, we can get the equation number 3 for the mesh third basically, and then we can represent all these three equation at one place, because in this equation number 3 we do not have any coefficient of I1, so we have taken it as 0 here, right? And similarly in equation number 1 also we do not have any coefficient of I3, so we have taken this as 0 here. So we can represent this in the matrix form like this. Now in this matrix, this particular matrix is the matrix A basically. Okay, so this matrix is used to determine the values of the unknown parameters. So let us see. So now we can find out the value of I1, I2, and I3 using the Cramer's rule in this way. And as we can see, that determinant A is used in all these three equations. So we'll find out the determinant of A. So A is given by this equation here, right? So we'll solve this equation to get the value of A. So it is 8 basically. Okay, this is 8. So now we'll find out the value of I1. So I1 can be obtained by obtaining the determinant of this particular parameter, matrix, square matrix. So we'll get this as 115 by 8 ampere, right? And then similarly I2. So I2 is here. This one, this matrix divided by determinant of A, which is 8, right? So we have got 70 by 8 ampere, and similarly we'll get the value of I3, so which is 55 by 8 ampere. So the purpose was to understand the application of Cramer's rule in the electrical circuits. Now uh, because the number of meshes were 3, so we have got three equations here, three algebraic equations, because of the number of meshes. So as the number of meshes increase, the number of equations also increase. So solving such algebraic equations using conventional technique of algebra is quite difficult. So for convenience, we have this Cramer's rule, which can be used to solve these electric circuit equations also, right? So this was about this particular numerical. So now let us see one more numerical, which is based on the star delta transformation. Now in this numerical, we are asked to find out the resistance, equivalent resistance across AB in this particular circuit. Now if you see this particular circuit, and if you assume that the current, some current is flowing in this particular branch, so that current would divide here, here, and then at this particular junction, and then meet at this junction like this. Okay, this is how it would be flowing. Now we cannot say whether these resistances are in series or in parallel. So this is the case of star delta basically. Okay. Now how it is star delta, let us see it with, let us solve this particular numerical. Okay. Now, as you can see here, so let us try to solve it. So we will mark these as this is A and this is B and this is letter C and this is letter D. Now you will ask me why I have marked it as A. So this is nothing, both are same because they are short, right? They are short, so this terminal and this terminal is same, right? So now we have this shape. If you see, this shape is a delta shape basically. So we can convert this delta shape into what do you say, a star basically. So let us convert this into star. So uh, let's draw the circuit here. So I'll draw a star and then I have this is my node C here, and then I have one more resistance connected here, and this is my node D, and then we have two resistances connected at B from C and D. Okay, so now this is what I have got. This is B and this is also A here. Okay, now earlier, now if you have seen it earlier, these three nodes were connected with the delta shape basically. So what I have done, I have converted this delta into star. Okay, so the purpose is to understand when we face such type of circuits, which method should we use, which circuit analysis should we use to simplify such bridge circuitries where we find some delta shapes or star shapes, right? Now in this, you have this one. Now when we convert delta into star, what do we do? So let us draw the same thing in between this one here, right? So from the derivations of star delta transformation, when you have to transform from delta to star, so in that case, this is, let us say, some resistance RA, this is, let us say, some resistance RC, and this is, let us say, some resistance RD, and it is 1 ohm here, it is also 1 ohm here. So RA is basically the resistance of opposite branches. This is RA. So product of these opposite resistances means 1 into 1 and divided by sum of all the three resistances of delta. So 1 plus 1 plus 1. So it is 1 plus 1 plus 1. So it is 1 by 3 ohm. So RA is equal to 1 by 3 ohm, right? Then we can find out RD also. So RD is this one. This is my RD here. So we'll multiply the opposite resistances. It is 1 into 1. And then we'll add all the three resistances of delta, 1 plus 1 plus 1. So it is again 1 by 3 ohm. And so RD is equal to 1 by 3 ohm, right? Now then you have RC. So RC is this resistance here. So 1 into 1, 1 by 3 ohm. So now this is also equal to 1 by 3 ohm, right? Now we have this circuit diagram, so we can simplify it. Now let us draw this circuit diagram here like this. You have junction node A, sorry, then you have uh, so this can be drawn like this. Now we can take this point as a neutral point, basically N. Okay. So for convenience, I'll take this as N because this is also a junction. So this is N here, right? From N to, you can see, from N to C, you have one resistance, which is RC. So from N to C, so this is, let us say, junction node C. So we have resistance RC, which is equal to 1 by 3 ohm. And then similarly from N to D, you have one more resistance, which is RD. So RD is equal to again 1 by 3 ohm. So this is, let us say, D here. Now C to B and D to B, there are two resistances. Okay. Now from C to B and from D to B also, that means this is short and this is a B point, right? So C to B and D to B. I mean, we have resistances of 1 ohm each. So this is 1 ohm and this is also 1 ohm, right? Now we can see here that okay, so we can see that this is RA, which is equal to 1 by 3 ohm. So we can see that these resistances, these two resistances are in series, and these two resistances are in series. So now simplification is like this. So we have A, and then we have a resistance RA, which is 1 by 3 ohm, and then we have split of branches. This is N, this junction is N, and this is 1 plus 1 by 3, and this is also 1 plus 1 by 3, and then we have the node B here. Now these two now are in parallel, you can see. These two are in parallel. So it is okay. So we'll have this parallel combination. So this is B, this is N, and this is A. This is RA is equal to 1 by 3 ohm, and this is, now these two values are 4 by 3. This is also equal to 4 by 3. So this is 4 by 3 parallel 4 by 3, right? Ohms. So the uh, equation here, the final equation will be, now you have this RA and this is a parallel. So this is, let us say, R dash basically. So R dash will calculate here. R dash is equal to 4 by 3 parallel 4 by 3. This is equal to, so now we'll simplify this equation. So we have got R is 1 by 3 ohm and R dash is 2 by 3 ohm. So these two are in series with one another. So this is a series combination here. Right, this is series. So we'll add these two resistances. So ultimately we have got that the equivalent resistance between AB is 1 ohm. So in this particular question, we have used the concept of star delta. So this will be very helpful for you to solve the electrical circuits, complex electrical circuits. So now this is it for today's lecture, guys. Thank you so much.